Hello everyone, welcome to my YouTube channel. In a previous video, we have solved some problems based on electric field intensity. Today we will discuss about electric flux density and we will solve some numericals based on it. Okay, so let us start with electric flux density. So as we know that in 1837, Michael Faraday performed the experiment of electric field. So here, if a test charge is placed near any point charge, suppose this is a test charge and which is placed near any point charge, then what happened? Then it experiences a force. Some force is acting on that. Okay, so here the direction of this force is radial and it is radiated outward from the positive charge. So these are lines of force. So these lines are called as flux lines, or we can say the streamlines. So that means there is an electric field around that charge. Okay, like this. So this electric field is in the form of small bunches which contains fixed number of electric lines of force. Such a bunch is called as a tube of flux and the total number of bunches is called as electric flux. This is phi. Okay, so here this electric flux is denoted by psi and it is a scalar field. So the density of electric flux is called as a flux density, which is a vector field, or we can say it is a vector quantity which is denoted by d bar. Okay, as we know that here electric field intensity is denoted by E bar and electric field flux density is denoted by d bar. Okay, so here we have studied that electric field intensity, that is E bar, can be measured directly, but the electric flux and the flux density are not measured directly. To understand this concept of electric flux, we will study the Faraday's experiment with the concentric spheres. So here consider one concentric sphere having a radius A. This is the circle concentric sphere which is having radius A, and this sphere consists of a charge plus Q. This is plus Q charge. Okay. Then this sphere is then placed in another sphere which is having radius r is equal to b, which can be shown in this figure. Then there is no electrical connection between this inner sphere and the outer sphere. So here an insulating or dielectric material is placed between two spheres as shown in this figure. So here the outer sphere is then connected to the ground momentarily to remove the initial charge present on it. Okay, so here the inner sphere which will consist of plus Q charge and then taken out and leaving only the outer sphere. So now if we will measure the charge present on this outer sphere, this is our outer sphere, then it will be equal to minus of Q. This is minus of Q and this is plus of Q. Okay, so there is no electrical connection between the two spheres. So you may ask us question, how the charge is developed on this outer sphere. Okay, so here the answer is very simple. There must be some electrical displacement between these two spheres, that is from inner sphere to outer sphere, and this electric displacement is taking place from this inner sphere to the outer sphere. So this electric displacement is shown in this figure by the lines which are drawn radially from one sphere to the another sphere. These are the lines. Okay, so because of this displacement, a charge of equal magnitude but having opposite sign is developed. So here you can see the inner sphere which is having radius r is equal to a and the outer sphere having radius r is equal to b. So here this inner sphere consists of plus Q charge, and due to that displacement an outer sphere consisting of again the point charge, that is equal to minus of Q. So here plus Q and minus Q, they are equal but opposite in direction. Okay, so here if the charge plus Q is present on inner sphere, then it is increased to charge minus of Q, which is developed on outer sphere and which is also in increases. Okay, so that means electric displacement is proportional to the magnitude of charge. So this displacement is not dependent on the medium between two spheres. And this electric displacement is called as the displacement flux, or we can say electric flux. That is nothing but psi. Okay, so here for the Faraday's experiment, psi is equal to Q. Since Q is the charge which is measured in coulombs and the unit of electric flux is coulombs. So in general we can say that electric flux originates from the positive charge and it terminates on the negative charge. Okay, so we can see this in figure 2.2.2. Here the flux lines travel from this plus Q to minus Q. That means here the electric flux originated from the positive charge and it terminates on the negative charge. This is positive and this is negative. So if the negative charge, that is minus Q, is absent, then the flux lines terminates to infinity as shown in this figure 2.2.3. Okay, so here there are some properties of flux lines. The first property is that the flux lines always start from positive charge and ends on negative charge. So we can see this is plus positive charge, that is plus Q, and it is terminate at the minus of Q, that is negative charge. If second property, if only positive charge is present and negative charge is not existing, then the flux lines terminate at infinity, like a figure 2.2.3. So here only positive charge is present. Okay, negative charge is absent. So that's why here the flux lines terminate at the infinite level. Okay, third property is that the flux lines never cross each other. These are the flux lines and these are never cross each other. Okay, then fourth property is that the flux lines are not dependent on medium in which the charge plus Q and minus Q are placed. Then fifth property, the total number of flux lines is called as electric flux, which is denoted by this psi, and electric flux is equal to the charge, that is total charge. Okay, and last property is the flux lines are always perpendicular and in radially outward direction. Okay, so these are the properties of flux lines. Then after that, let us move towards electric flux density. So as shown in this figure 2.2.1, this is figure 2.2.1, the inner sphere consists of charge plus Q, this is plus Q charge, and this charge produces electric flux that is equal to psi on the surface of this inner sphere, and the radius of inner sphere is, suppose r is equal to a, so its surface area is 4 pi a square. We know that the area of sphere is given by formula 4 pi a square. Okay, this is the area of sphere. So now electric flux, that is psi, is uniformly distributed over the surface area of inner sphere. This is the inner sphere. Okay, so the density of this electric flux is called as electric flux density, and it is a vector quantity which is denoted by symbol d bar. So this electric flux density is given by d is equal to electric flux divided by surface area. As we know that here the area of sphere is equal to 4 pi a square. So here we can calculate this d bar is equal to psi upon area, and the value of area is 4 pi a square. Okay, so here the unit of this electric flux density is what? As we know that this psi is equal to Q, so we can write here the unit of this psi is equal to Coulomb, and the area is nothing but meter square. So that's why the unit of this electric flux density, that is d bar, is equal to Coulomb per meter square. Okay, it is also called as the displacement flux density or displacement density. Okay, so here the direction of this d bar, that is electric flux density, at a point is the direction of flux lines at that point. So here the magnitude of this d bar is always equal to the number of flux lines crossing a surface which is normal to these lines divided by the surface area. Okay, so again consider two concentric spheres, A, that is the radius of this inner sphere, and B is the radius of outer sphere. Okay, so for the inner sphere the area becomes 4 pi a square, that is 4 pi a square, and for outer area or outer sphere the area is equal to 4 pi b square. Why? Because the inner sphere which is having the radius r is equal to a, and for outer sphere the radius is equal to r is equal to b. Okay, so in this case electric flux density is in the radial direction. So thus we can write the expression for d bar is equal to, for inner sphere it is d bar is equal to q upon 4 pi a square into ar bar. This is the equation of electric flux density in the form of vector. Why in the form of vector? Because here we have to multiply this equation into the unit vector, that is ar bar. Okay, in similar way we can write the equation of d bar is equal to q upon 4 pi b square into ar bar. This is for the outer sphere. So here this ar bar is nothing but the unit vector in the radial direction. So now at any radial distance r, we can write d bar is equal to q upon 4 pi r square. Okay, instead of taking a and b, we can directly write d bar is equal to q upon 4 pi r square into ar bar. Okay, here the value of r is nothing but b minus a. Okay, then after that let us move towards the relationship between d bar and e bar. So for that, consider that inner sphere, that is r is equal to a, which is shown in this figure, and this inner sphere is becoming smaller and small, but it is still maintaining a charge plus q. Then in this case the inner sphere acts as a point charge. Okay, so here q lines of flux are directed outward from this point charge, and these flux lines are passed through an imaginary spherical surface of area 4 pi r square. So the electric flux density from this point charge at a distance of r meter is given by d bar is equal to q upon 4 pi r square into ar bar. Okay, now we know that the electric field intensity at a distance of r meter from the point of charge, which is given by E bar is equal to q upon 4 pi epsilon 0 r square into ar bar. So this is the equation of E bar in the free space, for which the value of epsilon r is equal to 1. So we can write E bar is equal to E bar epsilon 0 is equal to q upon 4 pi r square into ar bar. So if we compare the left hand side, the equation with 2.2.6 with the equation number 2.2.8, then we can write left hand side is equal to E bar epsilon 0, because the right hand side is same. Okay, so here we can write d bar is equal to epsilon 0 E bar, that is it gives the relation between electric field intensity and electric flux density in the free space. Now if the medium is not free space, then we can write d bar is equal to epsilon E bar. Here the value of epsilon is epsilon 0 epsilon r. The value of epsilon 0 is 8.854 into 10 raised to minus 12 farad per meter. That is permittivity of free space, and epsilon r is the relative permittivity of the medium, which is having value 1 for the air medium. So we can write d bar is equal to epsilon 0 into epsilon r into E bar. So as d bar and E bar are related as d bar is equal to epsilon 0 E bar, we have derived equation of E bar for standard charge configurations. So by using this relation we can develop equations of d bar. Okay, so here for charge configuration the first point is infinite line charge. The electric field intensity due to infinite line charge is given by E bar is equal to rho L upon 2 pi epsilon 0 r into AR bar, and electric flux density for same infinite line charge is given by d bar is equal to q upon 2 pi r into AR bar Coulomb per meter square. Second condition is for the infinite surface charge. The electric field intensity for the surface charge is given by E bar is equal to rho s upon 2 epsilon 0 a 0 bar, and for flux density it is given by rho s upon 2 into an bar Coulomb per meter square. Third condition is for volume charge, that is electric field intensity due to volume charge is given by E bar is equal to integration over closed volume V rho v AR bar upon 4 pi epsilon 0 r square into dV, and for flux density the formula for d bar is equal to integration over closed volume V rho v dV upon 4 pi r square into AR bar into Coulomb per meter square. Okay, so this Coulomb per meter square is nothing but the unit of this d bar. Okay, so these are the three formulas for the infinite line charge, infinite surface charge and infinite volume charge. This second column is for electric field intensity and third column is for flux density. Okay, then after that we will solve here one problem based on electric flux density. Okay, so the one's question is there, a point charge q is equal to 20 nanocoulomb is placed at the origin in Cartesian coordinate system. Find the electric flux density, that is we have to calculate here d bar at a point P having coordinates 1, -2, -4 meter. Okay, so here we have the equation for electric field intensity due to the point charge, that is E bar is equal to q upon 4 pi epsilon 0 r square into AR bar. This is the basic equation of electric field intensity due to the point charge. Okay, but here we want to calculate the electric flux density. So for that we have to derive here the formula for electric flux density, that is equal to d bar is equal to epsilon 0 E bar. Okay, so here we will get formula for electric flux density, d bar is equal to epsilon 0 into E bar. Means what happened here, we have to take here d bar is equal to the value of E bar is as it is into we have to multiply this equation with the epsilon 0, then this epsilon 0 and epsilon 0 get cancelled and the remaining equation is q upon 4 pi r square. Okay, so here we have to just remove the epsilon 0 value from the denominator side and we will get here value of d bar. Okay, then after that here the point charge is given having value 20 nanocoulomb, that is 20 into 10 raised to minus 9, because here nano means 10 raised to power minus 9. Okay, this is 10 raised to power minus 9 for the nano value, and r is nothing but it is the distance between q and p. So see here first, here the point charge is given. So let us consider this is point charge which is placed at the origin. So that's why the coordinates of this point charge becomes 0, 0, 0, and suppose this is the point P having coordinates 1, -2, -4. Okay, this is 0 point, this is O point, or we can say point charge, and this is the point P. Okay, so here we have to calculate electric flux density at this point. That means what? Here the vector is formed and the starting point of this vector is, this is original point, origin point considered as O, and this is P point, that is reference point. So here we can consider this O as a starting point and P as a ending point. Sorry. So this is the starting point and this is P, ending point. So here if you want to calculate the vector, then we have to use here OP bar is equal to P bar minus O bar. That means ending point minus starting point. We know the coordinates of ending point, that is nothing but 1 comma minus 2 comma minus 4. Okay, so here we can write R is equal to, that is unit vector or the distance between O and P, which is given by this R bar, is equal to ending point is 1 comma minus 2 comma minus 4. Then we have to just subtract the origin point, that is 0. So we'll get 1 minus 0 square plus minus 2 of minus 0 square plus minus 4 minus 0 square. Okay, like this. Okay, so here we will get under root, the mod of R is nothing but the distance between the P and O, that is origin and the reference point, which is equal to 1 square plus 4 square 2 square plus 4 square is equal to root 21. Okay, we have to just put all these values in equation number 2. D bar is equal to, the value of Q is given, that is equal to 20 nanocoulomb upon 4 into 3.14, and the value of AR bar is unknown. So we have to calculate this by using unit vector concept. So we can calculate here the value of R bar, that is equal to AR bar is equal to R bar upon mod of R bar. Okay, so here the value of the unit vector AR bar is equal to AX bar minus of 2AY bar minus 4AZ bar. This is the value of R bar divided by the value of mod R is 21. Okay, so after putting the value of AR bar and R bar in the equation number 2, we will get value of D bar is equal to 1.82 into 10 raised to minus 11 AX bar minus 3.64 into 10 raised to minus 11 AY bar minus 7.27 into 10 raised to minus 11 AZ bar Coulomb. So this is all about our today's session. I hope you will like and enjoy. अगर आपके कुछ डाउट या सजेशंस होते हैं तो आप हमें नीचे कमेंट बॉक्स में लिख सकते हैं. So we will stop here with motivational quote. Today's motivational quote for you is, don't limit your challenges, challenge your limits. Thank you for watching my videos. Please like, share and subscribe to my channel. Thank you so much.